There's a lot of really rich information in the Jacobian matrix, and we can use it as a sort of diagnostic tool to work out how well the robot can move at a particular joint angle configuration. Let's look in more detail at the case where the Jacobian matrix is singular, and this is what the Jacobian matrix looks like for a robot in the pose shown here, where joint angle 5 is equal to 0. The motion of the end effector due to joint 4 is given by this column of the Jacobian matrix, and the motion of the end effector due to joint 6 is given by this column of the Jacobian matrix. You'll notice that these two columns are identical, and that means that they result in the same end effector motion, and in this particular case it is rotation about the world z-axis. We can get the same motion by changing joint 4 or by changing joint 6. For a square matrix, if two columns are identical, then it becomes singular. A mathematician would say that the rank of the matrix has reduced from full rank, rank 6, to a rank of 5. Here is that same Jacobian matrix in MATLAB, and we can clearly see that columns 4 and column 6 are identical. If we compute the determinant of the matrix, we see that it is equal to 0. It means that this Jacobian is singular. If I compute the rank of this matrix, it's equal to 5, and that's saying that there are only 5 unique columns in this matrix. 2 of the columns are identically equal. Let's look now at a more healthy Jacobian matrix. I'm going to compute the Jacobian for the set of joint angles Qn. This matrix has no obvious duplicated columns, its determinant is not equal to 0, and its rank is equal to 6. That means that all 6 columns are unique. In the last lecture, we introduced the concept of the velocity ellipse, and we did this in 2 dimensions. For a set of joint angles which lie on a circle in the plane of all possible joint angle velocities, we map that into an ellipse in the space of all possible end effector velocities, and that indicated that in a particular robot joint angle configuration, the robot was able to move more quickly in the world y direction than it could move in the world x direction. We can do the same thing for a 6-axis robot, but the mathematics is a little bit more complex. We have this relationship between the robot end effector spatial velocity and the joint angle velocity. I can combine these two equations and come up with this expression, which is the equation for a hyperellipsoid that's an ellipse in 6 dimensions. It's a little hard to get your head around, but mostly we're interested in the first 3 elements of the spatial velocity. That's the translational velocity of the robot end effector. And in this case we end up with a 3-dimensional ellipsoid which we can quite easily plot. So here is the velocity ellipsoid for a robot in a particular configuration. And we can view this ellipsoid from different angles, and we can see that the ellipse is quite elongated in the vertical direction, and it's reasonably flat in the direction towards the base of the robot. And so the robot is able to move most quickly in the direction of the long axis of the ellipse, and it moves much more slowly in the direction of the short axis of this ellipsoid. If the ellipsoid was actually a sphere, then we say the motion is isotropic. That means that the robot end effector is able to move equally quickly in any direction. It's convenient to introduce a notion of manipulability, difficult word to say, and it's a simple scalar measure that says something about the shape of the velocity ellipsoid. If manipulability is equal to 1, then we have the case of isotropic motion. The robot is able to move equally fast in any direction. If manipulability is equal to 0, then the ellipsoid is collapsed and it becomes just an elliptical plate. And that means that motion in one Cartesian direction is not possible at all. In general, the manipulability will be somewhere between 0 and 1. If it's close to 1, it means that the robot is configured to move quite quickly in any direction in its workspace. As the manipulability gets closer to 0, it means that the robot is in an awkward pose, and there are some directions where it's not able to move very quickly at all. Manipulability is a strong function of the robot joint angles. So depending on the task, you may need to set the robot joint angles so that it has got the speed required in order to achieve that particular task. We're going to use MATLAB to display one of these velocity ellipsoids. The first thing I'm going to do is to plot the robot in the joint angle configuration that's in the middle of its workspace, and that's what the robot looks like. and then I'm going to use the method of ellipse to overlay on that a velocity ellipsoid. This method's got quite a number of arguments and options. First of all, I pass in the joint angles that I'm interested in. I want the ellipse to be plotted in the color blue, and I want the edge lines on the ellipse to be in white, and I want the whole thing to be somewhat translucent, so I'm going to give it an alpha value of 0.5. And there we see the velocity ellipse. Now I can rotate this around and look at it from all sorts of different orientations and viewpoints. If I look at it pretty much side on, we can see that the ellipse is relatively thin in the direction toward the base of the robot. So that's the direction where the robot is not able to move very quickly, whereas in the vertical Z direction, basically up and down, the robot is able to move quite quickly. So that's the velocity ellipsoid for this joint angle configuration. If I choose a different joint angle configuration, this is where the robot arm is stretched right out horizontally, which is the joint angle vector QS in my workspace, then the robot is in that configuration. And now I'm going to plot the ellipse for this particular configuration. So I'll just come back and edit this command, change QN to QS, and here we have the velocity ellipsoid for this particular case. Now we can see that it is an ellipse, but side on it's got no thickness at all. It is a plate. So in this particular joint angle configuration, the robot is able to move its end effector from this particular view up and down and left and right, but looking at it this way, it has got no ability at all to move the end effector back towards the base.